Imagine a library that holds every book ever written, every scientific paper published, and the entirety of the internet's public discourse. Now, imagine trying to hold that entire repository of human knowledge inside a single, unified brain. When you interact with a system like GPT-4, you aren't just talking to a clever script, you are engaging with a mathematical structure composed of over 1 trillion parameters. To put that in perspective, if each parameter were a single grain of sand, you would have enough to fill a massive warehouse from floor to ceiling. It is easy to get lost in the sheer scale of these systems. We often hear about trillions of parameters, but that term can feel abstract. Think of it like a giant soundboard with a trillion sliders. As the model consumes vast amounts of text, it tweaks these sliders, ever so slightly, until the patterns it identifies become incredibly precise. It is not just rote memorization. Data suggests that these models begin to grasp the underlying structure of logic itself. Yet, there is a lingering mystery at the heart of this technology. You will find massive tables of floating point numbers. Experts predict that this illusion of intelligence is actually an emergent property, a phenomenon where simple, repetitive mathematical operations, when scaled up to a massive degree, suddenly manifest behaviors that look remarkably like comprehension. We are standing at a unique intersection of advanced mathematics and linguistics, where the boundaries between statistical probability and genuine insight are blurring. But a trillion parameters don't manage themselves. To understand how this architecture avoids chaos and maintains coherence, we need to peel back the layers of the transformer, the fundamental engine driving this entire revolution. To grasp that architecture, we first have to look at the evolutionary lineage of machine learning. If we rewind to the early days of artificial neural networks, the landscape looked vastly different. These systems were mathematically elegant but rigid. They struggled with nuance, context, and anything approaching the complexity of human language. As research shows, the pivot arrived when we started stacking these simple nodes into deeper, more complex layers. This led to the era of recurrent neural networks, or RNNs. But this approach hit a wall. Because RNNs processed information one token at a time, they couldn't easily parallelize tasks. It was like trying to read a novel by looking through a straw. Data suggests that the field was essentially stuck in this bottleneck for years, waiting for a fundamental shift in how we represent relationships between pieces of information. Instead of forcing a model to read linearly, the transformer architecture introduced a mechanism called self-attention. This allowed the model to look at every word in a sequence simultaneously, weighing the importance of each word relative to every other word, regardless of how far apart they were in the text. We could feed massive amounts of data into these models in parallel, utilizing the raw power of modern GPUs to train on scales previously thought impossible. This architectural breakthrough is exactly what allowed researchers to move from models with a few million parameters to those boasting hundreds of billions. Yet, this leap in scale introduced a new set of logistical hurdles, because while the transformer provided the blueprint for growth, it also created an immense challenge in how to physically distribute and synchronize that knowledge across a sprawling network of hardware. To make sense of this physical distribution, we have to zoom in on the fundamental unit of an LLM's intelligence, the parameter. If you imagine the model as a massive, complex soundboard, the parameters are the thousands of individual knobs that determine the output. These filters are essentially matrices, grids of numbers that define the strength of connections between different concepts. Each individual number in that grid is a weight, a value that has been painstakingly tuned through massive amounts of training data. During the training phase, research shows that these weights shift and adjust, settling into values that allow the model to predict the next token with high precision. But here is where the sheer scale creates a bottleneck. A single matrix might contain billions of these weights, and performing the necessary calculations on a standard processor would take an eternity. Unlike a traditional computer processor, which is designed to handle a few complex tasks in sequence, a GPU is built for massive parallelization. Think of it as a vast, synchronized army of thousands of tiny calculators working in perfect unison. Instead, it feeds the entire input through these matrices simultaneously. The GPU slices the data into small, manageable chunks, distributing the math across its cores so that the entire transformation happens in a fraction of a second. Data suggests that this is not just about raw speed, but about architectural efficiency. It is a delicate dance of hardware and mathematics. The weights remain static in memory until an input triggers a cascade of multiplications. Because these operations are independent, the hardware can execute them in parallel, effectively turning the model's vast knowledge base into a fluid, responsive stream. Once the model outgrows the physical memory of one GPU, we encounter the next critical hurdle: how to split this mathematical web across multiple devices without breaking the logic that holds it all together. To bridge that gap, we shift from the architecture of the model itself to the efficiency of its execution. When you don't have a warehouse full of H100s at your disposal, the bottleneck is almost always memory bandwidth. In its training phase, a model typically lives in high-precision floating-point numbers, requiring massive storage for every single weight. But during inference, we can perform a clever sleight of hand. It is essentially the difference between storing a high-resolution, uncompressed photograph and a finely tuned JPEG. You lose a microscopic fraction of precision, but the file becomes portable enough to live on consumer-grade hardware. This reduction doesn't just save space, it accelerates the entire pipeline. Because the data is lighter, it travels faster between your memory banks and the processor cores. Not every neuron in this vast digital brain needs to fire for every query. Instead of lighting up the entire network, the model identifies only the most relevant pathways required to answer a specific prompt. It's an exercise in surgical precision, knowing exactly which parts of the model to activate and which to leave in the dark. Ultimately, managing billions of parameters isn't about brute force, it's about clever orchestration. We rely on quantization to compress the knowledge, and sparse activation to ensure that we are only spending computational currency where it truly matters. Looking ahead, the trajectory of this field is moving toward even more extreme efficiency. We are nearing a future where the most capable artificial intelligences will run entirely on the edge, residing on your phone or laptop without ever needing to ping a cloud server. If you found this exploration of technology fascinating, consider subscribing for more deep dives into the mechanics of the digital world.